Today I'm going to walk you through a cyclic voltammetry experiment, which I use to explore the redox properties of my molecule. I start by turning on my cyclic voltammetry software, and then I thoroughly clean my electrodes. We have a reference, counter, and working electrode. I start by cleaning the working electrode with micro polish and water. The working electrode is made out of platinum, and this is where the reduction and oxidation reactions will occur. A voltage will be applied to the working electrode, which will cause redox active species in the solution to gain or lose electrons. These electrons produce a current. I then clean the counter electrode, which is also made from platinum. The counter electrode completes the circuit and allows the current that gets produced to flow throughout the circuit and be measured. Finally, I clean the reference electrode, which is made from silver. The reference electrode has a stable potential that is used as a reference point against the potential of the other electrodes. Now I prepare my blank solution, which will contain just my solvent and the supporting electrolyte. I use a 10 milliliter beaker as my electrochemical cell. I add the supporting electrolyte to help the current flow through the solution. I dissolve this in my solvent, which is DMF, or dimethylformamide. Then I add my electrodes to the cell and connect all the electrodes to the potentiostat, which is the device that applies a voltage to the working electrode. This is called a blank solution because it does not contain the molecule that I am testing. In a cyclic voltammetry experiment, you apply a voltage to the working electrode. This voltage causes redox active species in the solution to gain or lose electrons. These electrons create a current. The current that gets produced gets measured and plotted along the y-axis on a cyclic voltammogram. The x-axis is the voltage that gets applied. The top part of the graph represents the forward scan. This is where the voltage is increasing, and it's where oxidation occurs. The bottom part of the graph represents the reverse scan. This is where the voltage is decreasing and reduction occurs. Here, the molecule gains back the electrons that it lost during oxidation. Now that I've finished the blank scan, I can add my molecule to the electrochemical cell. My goal is to see if this molecule can be oxidized and reduced without significantly degrading. I set up my electrochemical cell just like I did for the blank solution, but now I add my molecule to see if any new signals are produced. On the cyclic voltammogram, the top peaks that we see represent the current that's produced when oxidation occurs in my molecule. The bottom peaks represent the reduction of the molecule. Finally, I have to add an internal standard called octamethylferrocene. This standard provides a reference point because of its predictable and stable oxidation and reduction, as you can see on the graph here. The top peak represents the oxidation of the octamethylferrocene. The bottom peak represents the reduction. They are equal in size because the octamethylferrocene can lose and gain electrons without degrading. Overall, this experiment showed me that my molecule cannot be reversibly oxidized and reduced. I say this because the oxidation peaks are significantly greater than the reduction peaks. This implies that the molecule is not able to gain back all of the electrons it lost during the oxidation process. There are many more insights that I could gain from this cyclic voltammogram, but this was just a discovery experiment for me.